Finally, Webb's analysis of TRAPPIST-1d, the most massive black hole ever discovered. New Hubble images of Comet 3I Atlas. And in SpaceBites Plus, staring right down the jet of an actively feeding supermassive black hole. All this and more in this week's Space Bites. All right, this is it. This is the moment we've all been waiting for. Webb has been looking at the planets one by one in the TRAPPIST-1 system. The best place we could look for Earth-like worlds orbiting around a red dwarf star. We've got 7 planets in the system, all of which are about the size of the Earth. 3, maybe 4 of them are orbiting within the habitable zone of the red dwarf star. And so we've got chance after chance after chance to find some kind of Earth-like planet. And finally, when Webb arrived, it was the right machine capable of being able to observe atmospheres on exoplanets. We've already seen many examples of exoplanets that have been studied by Webb, and we've seen more chemicals in the atmospheres than any method has ever shown before. We see carbon dioxide, water vapor, methane, and other trace gases and elements in the atmospheres of exoplanets. And so you take the perfect machine, you bring it to the perfect star system. What do we find? And so far, nothing. So the closest 2 planets to the TRAPPIST-1 star, these are TRAPPIST-1b and TRAPPIST-1c. And it was always assumed that this was a very long shot chance to be able to detect anything, but the hope was that you would get something like a Venus, where you've got these Earth-sized worlds orbiting close to the star. They're superheated, thick atmospheres of carbon dioxide, but they pretty conclusively have been found to have no atmosphere. And that's not very surprising because TRAPPIST-1 is a super flare star, which means that it generates a tremendous amount of flare activity that would scour the atmospheres off of any planets that are too close. And of course, in a red dwarf system, the planets are very close to the star. So TRAPPIST-B and C seem to have no atmospheres at all. So they're not like Venuses, they're more like Mercuries, Earth-sized Mercuries. No problem. Now, the first planet that is just barely within the habitable zone is TRAPPIST-1d. And I say barely because it's in the habitable zone in the same way that Venus is in the habitable zone of the sun. So it was expected that it would be very hot, maybe have a very thick carbon dioxide atmosphere. And back in November 2022, astronomers did their first observations of TRAPPIST-1d with James Webb. And what did they find? Well, it took a long time for them to finally get the results. We've been anticipating this day for a very long time. And the results are no atmosphere detected. Now, this doesn't mean there's no atmosphere. It just means that there was no atmosphere detected. There's a couple of possibilities that could explain that. One is that it's much more like Mars, where you've got this incredibly thin atmosphere. It's just not enough atmosphere to be able to make this detection. But the other possibility is that it's actually a very thick atmosphere like Venus, but just such a thick layer of clouds at the top that it's obscuring any of the elements underneath. And we didn't get any detection of carbon dioxide or methane or water vapor in the atmosphere. And this is a really tricky observation. And we're going to talk another story where we're going to talk more about why it's such a tricky observation. It's at best inconclusive, and at worst, there's just no atmosphere there at all. But it's still early days, and astronomers are still developing their techniques on how to be able to make these kinds of observations. And I had a fantastic interview with Megan Gianluca earlier this year, where she went through each of the planets in order and gave us sort of a sneak peek of what we might expect with TRAPPIST-1d. And so, the good stuff is still coming. Once we get on to E and F and G, which are much more firmly in the habitable zone around this star. So don't be disappointed yet. Stay tuned. There's more coming. But if you want more information, we've got a story about this by Evan Goff. It's got a section about the process of elimination that the astronomers went through to get to this null result. So definitely check out that article. Now, speaking of TRAPPIST-1, we've got more information about the star itself. And this is Probably the biggest challenge that astronomers are dealing with is that because TRAPPIST-1 is a flare star, in other words, it puts out a lot of very powerful flares, very active, it's really difficult to distinguish what is the signal of the light that's coming from the planets around the star and the activity on the star itself. Once you get a sense of just how active the star is, then you can set that as a baseline to then tease out the atmospheric information of the planets in orbit around it. And we know that the star is covered by various magnetic features. You've got sunspots, you've got faculae, you've got areas of convection, and that magnetic fields that are twisting and turning. And this is all contributing to the changes in brightness of the star. And so researchers were using Webb to study the flares on the star. And then they discovered that after every flare, there's a slight brightening that's actually caused by the disappearance of magnetic features on the surface of the star. And that was exactly the observation that they were looking for, to be able to set a baseline, to be able to understand what is the intrinsic brightness of the star, when are we seeing a flare or some kind of magnetic event on the surface of the star, and when are we just seeing just the baseline brightness of the star, and how can we tease out those planets. And so this means that astronomers have made big progress on this most challenging part of this process, and this will help them to observe and understand not only the TRAPPIST-1 system, but other star systems when they're trying to observe the atmospheres. And this will even play out into future observatories when we're trying to observe Earth-sized worlds orbiting around sun-like stars. So if you want to learn more about that process, check out the story by Mark Thompson. All right, let's move on to Comet 3I Atlas, which is the third interstellar object to pass through the solar system. And unlike the previous two, Oumuamua and Borisov, 3I Atlas, we are seeing it inbound into the inner solar system, but it is moving faster than any interstellar object that we've seen so far to date. It was first discovered at 6 astronomical units, and now it's about 3.5 astronomical units away. And its coma, the ball of gas and dust around the central nucleus, and the tail are starting to form. And one really interesting observation that's already been made is that we're seeing a lot of water coming off of this comet. So right now we're seeing about 20% of the surface area of Comet 3I Atlas starting to sublimate water. And normally a comet within the solar system, say from the Oort cloud, is only giving off between 3 and 5% of its surface is giving away water when it's this distance away from the sun. This is surprising. And this is a really interesting observation, because this says, okay, maybe Comet 3I Atlas came from a star system that had much lower metallicity than the sun. And so you have less heavier elements. You don't get all of the rock and debris that's mixed in with the comet. Instead, it's a lot more pure water ice and other volatiles. This is going to be really interesting as the comet gets closer, as it reaches higher amounts of sublimation from the radiation coming from the sun. And then astronomers are going to be able to watch it through this entire process once it crosses that closest point and starts to move away from the sun again. How quickly will that tail die down? You'll get even more information about the star system that the comet came from. One other thing is that normally at this point, when you see a comet, you see cyanogen gas coming off the comet. In fact, about 100 years ago, there was a big scare that there's cyanide coming from comets. But normally at this point, you see cyanogen gas coming off of the comet. And yet so far, we don't see any of that gas. And so again, that might be part of this explanation about the origin of the system itself. We've got a longer story about that by Andy Thomaswick. And of course, the Hubble Space Telescope has joined in the fun and taken its first images of Comet 3I Atlas. So here is your picture of 3I Atlas taken by Hubble. And this picture was taken at 3.8 AU. So it's now at 3.5. So it was a little farther away when it took this one. But already you can see the coma, all of this gas and dust is starting to surround the central nucleus of the comet. And of course, as we said, a lot of this, a surprising amount of this is water. And you're starting to see that tail start to form. And this is just going to get bigger and bigger and bigger. As it gets closer to the sun, there's more radiation pressure. It's starting to push away this material. you're going to see that big, wonderful tail from an interstellar object. Thanks to the Hubble images, astronomers are estimating that it's losing between 6 and 60 kilograms of dust every second, and they're able to do a much better estimate of the size of the nucleus. They estimate that it's no bigger than a radius of 2.8 kilometers. So thanks to Hubble, we're learning a ton more about this. And again, like we're still, it's not going to get to its closest point until October. It's got lots more time to study this object as it gets closer and closer and then gets farther and farther. And so if you want to learn more about the Hubble observations, check out the story by Mark Thompson. All right, let's go back to talking about little red dots. And these are these bizarre objects first discovered by James Webb. What do we know about them? They are bright and they are early. They're within the first billion years after the Big Bang. And they're putting out a surprising amount of radiation in a very tight place. And so how do you get that much radiation from such a small grouping? Like they probably have about 1/10 the size of a galaxy like the Milky Way. One possibility is that you've got a supermassive black hole that is starting to feed and is putting out large amounts of radiation. The other possibility is that you've just got a very compact galaxy where you've got lots of stars in a small area. Imagine a very big globular star cluster. But as we talked about last week, if it is a supermassive black hole, not only would you expect to see large amounts of the radiation seen by Webb, but you would detect the radiation with other telescopes in other wavelengths, like in X-rays, and we don't see that. But it's really difficult to get a lot of stars into a small, compact area. A new paper has come out that proposes that the reason we're able to get a very compact grouping of stars is that there's actually a very rare type of larger dark matter structure that is rotating very slowly. And so if these things are rotating very quickly, which is what is more common, then you get this centripetal outward force that causes the galaxy and the stars to get more distributed. But if it's very slowly rotating, then all of the stars sink down to the heart of this larger dark matter structure. They're denser. And so that might help explain why you can get all of those stars that much closer together. Who knows? The quest to understand these little red dots goes on, and we still have decades left to try and figure this out before we lose Webb. And we've got a story on this from Mark Thompson. Now it seems to be the most massive black hole ever discovered. Just for comparison, the supermassive black hole at the heart of the Milky Way, Sag A star, contains 4.1 million times the mass of the sun. That is a lot, but actually, as galaxies go, that's not very much. There's probably 100 million solar mass black hole at the heart of Andromeda, and astronomers have found ones that have billions of times the mass of the sun. And now they think they found the most massive, one with 36 billion times the mass of the sun. The supermassive black hole is at the center of the cosmic horseshoe, and this is thought to be one of the most massive galaxies that are in the entire observable universe that we know of. And the gravity around the cosmic horseshoe is so strong that it has a beautiful Einstein lens surrounding it, where you've got almost this perfect circle of gravitational lensing around this galaxy. Astronomers have used several methods to try to measure the mass of the black hole at the heart of this galaxy. Like, they assumed it was going to be massive, but just how massive? And so one method is that they measure the pathways that the light is taking, that as it gets closer to the center of the galaxy, it's pulled by the supermassive black hole, and that allows you to measure how much mass is pulling on that light. That's one method. The other method is to be able to actually measure the movements of the stars at the center of the galaxy, and they're going very fast. In fact, this is how they discovered the supermassive black hole at the heart of the Milky Way. You measure the movements of these stars as they're orbiting nothing. They did the same thing with the cosmic horseshoe and measured the stars moving 400 kilometers per second around nothing. You take the two methods, you check them against each other, and that's how they came up with this mass of 36 billion times the mass of the sun. I'm sure this record will be broken again, but still very interesting. And you can learn more about the method they used to figure this out by reading the story from Evan Goff. When our sun dies, it will become a white dwarf star. Really, it's going to puff off all of its outer layers, and you'll be left with the core of the sun, where all the fusion is happening today. And that accounts for about 50% the mass of the sun. So that's a white dwarf. And if a white dwarf eventually feeds off some partner star and gets up to 1.44 times the mass of the sun, then it can no longer remain stable and it explodes as a type 1a supernova. And astronomers have found white dwarfs with various masses in between, but now it looks like they found the most massive white dwarf with 1.2 times the mass of the sun. So how did it get that massive? Well, one possibility is that it fed off some partner star and isn't doing that anymore. But the other possibility is that it merged with another white dwarf star. And some really valuable clues there. When astronomers observed this white dwarf, they detected the presence of carbon in the atmosphere of the star. And when you detect carbon, which is a heavier element than the hydrogen and helium you expect to see on the surface, then that means that the white dwarf probably consumed planets, asteroids, comets, things like that. But not only do you see carbon, you see other heavier elements like silicon or neon. But in this case, they didn't find those heavier elements. And so it appears that you got two white dwarfs that merged to become a 1.2 solar mass white dwarf, but didn't gain enough mass to cross that Chandrasekhar limit of 1.44 times the mass of the sun, which would cause it to detonate as a type 1a supernova. We've got a story about this from Evan Goff. Every week we do a vote on our channel where you tell us what you thought was the best space news story of the week, and the winner this week was what? What a surprise! Planet found at Alpha Centauri. Thank you everybody who voted last week. We're going to put a vote to this week's stories into the post tab on our YouTube channel. So if you are just scrolling through YouTube and you see the vote, just take a second and just let us know what you thought was the best story. And then we will count them all up and we will celebrate next week. Of course, the best chance, subscribe to the channel, click on the notifications bell, and then train the algorithm. On to Mars. One of the big challenges in driving a rover around on Mars is the regolith. And we learned this when NASA's Spirit rover got stuck in the sand as it was trying to go across an area on Mars. Its wheels got stuck. It wasn't able to point its solar panels towards the sun, and then it wasn't able to keep itself warm during the night on Mars, and it died. So don't get caught in the sand is like rule number one for Mars rover drivers. And they take a lot of care when they are planning out their routes. Does that look like sand? Let's avoid it. Try to stay on the rock, take the long way around. It's really tricky to simulate the sand on a world that has a much lower gravity than we have on Earth. You can reduce the weight of your rover. You tie ropes to it and then it appears like it's 1/3 the normal weight is what it would feel like when it's on Mars. But you can't change the weight of the individual particles of the sand, and the sand changes differently when it's in a lower gravity environment. You have different amounts of friction. You have different ways that the sand moves and flows. And that's, again, why Spirit got caught. And so researchers are now trying to split the difference. They've developed a really cool simulation on computer where they simulate the effect of a rover going on sand. They are able to simulate the particles of the sand, and then they compare what their simulation tells them to what they actually see when they drive the rovers around in the real world, and then compare that to what they've learned about driving around on the surface of Mars. And we should get to a place where we can either have better designs for wheels or be able to better recognize the areas on Mars that are going to snarl up rovers if they happen to drive across it. We've got a story about this from Evan Goff. All right, now some really cool pictures from Mars. So first up, this is an image of the Archean Fosse region taken by the European Space Agency's Mars Express spacecraft. This spacecraft has been there for decades, taking really cool pictures of the surface of Mars. And this is a very special terrain. It has a region of deep cracks and valleys with alternating chunks of raised and lowered ground. And this creates this jagged landscape where you've got these cracks and ridges that can run for hundreds of kilometers, and they can go down to depths of a couple of kilometers. And it's believed that this region was created about 3.7 billion years ago when there was still a lot of volcanic activity on Mars. You had this volcanic uplift that was raising up one chunk of Mars, and you got cracks on the edges of where this was happening. This wasn't the end of the activity in the region, because planetary scientists, when they look at these images, can see evidence that there were rock glaciers moving through this area, continue to scour the bottoms of these cracks. And there are no glaciers in this region on Mars today, but we know that the axial tilt of Mars changes pretty dramatically over time because it doesn't have a large moon to keep it stable. And so the axial tilt of Mars can sort of roam back and forth. And there was a time in the past where this region was more oriented to a place where there were glaciers operating on the surface of Mars, and then other times when it was tilted away and you didn't get glaciers. And so just by looking at this region on Mars, scientists are able to do detective work to figure out what the climate was on Mars in the past. We've got a story about this by Mark Thompson. And this picture is great. This is taken by the Perseverance rover. It's actually captured back in May on a day where the air was really, really clear on Mars. Engineers at NASA had Perseverance use its mass cam and take 96 pictures in a circle around itself, and then they stitched that together into this single mosaic. And there's a lot of interesting features in this. The hills are about 65 kilometers away and sort of give you a sense of perspective on how far you can see on the surface of Mars. And then there's a whole bunch of rocks, some which are relatively close. And in fact, Perseverance had recently taken samples from those rocks. In one of the rocks in this picture, it had taken its 43rd sampling drill. So it just shows sort of how busy Perseverance has been on the surface of Mars. We've got a story about this by Matt Williams that goes into a lot more detail about all the individual objects that you can see in this picture. Now, you're watching this week's Space Bites, and you know, there's a lot of space news in it, but this is just a fraction of the space news that we're covering at Universe Today. For example, astronomers have detected the most distant fast radio burst ever. This is a fast radio burst that was detected when it was just 3 billion years after the Big Bang. And then another story about how artificial intelligence could be used to prevent satellite collisions. There's so many satellites that are orbiting around and they're getting closer to each other on a regular basis. How can we develop algorithms that can keep them from crashing into each other? And then astronomers capture the rare birth of black hole activity. We actually have seen a supermassive black hole switch from being quiescent to active within the time of its observations. Now, these are just some of the stories. There's many more that we're working on. I write a weekly email newsletter that goes out on Fridays. I write every single word in it, by human for humans. It is completely free. We don't put any advertisements in it. You can go to university.com/newsletter to sign up. All right, are you enjoying Space Bites, but you wish there was just one more story? Well, good news. There is. It's called Space Bites Plus. We offer it totally for free with no ads over on Patreon. And this week's bonus story, The Eye of Sauron, a supermassive black hole jet pointed directly at the Earth. And I'll put a link in the show notes so you can just watch it right now. I'm going to talk about CLICKBAIT in a second, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Bradley Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bielak, Cy Nelson, David Gilton, David Matz, Evan Pro, Greg Feely, Hudson Moore, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Marcel Smith, Michael Purcell, Monzo, Nick Borquez, Nick Solari, Paul Robach, Rinkaidu, Robeck, Sean Sargent, Stephen Fowler Munley, Vlad Chiplin, and Wolfgang Klotz, who support us at the Master of the Universe level, and all our patrons. All your support means universe to us. Every week, no matter what we do, we get people accusing us of doing clickbait. Last week was probably some of the most complaints that we got. On the one hand, people didn't like us having a picture of me look like a blue avatar / Aang the Last Airbender, and that I was humiliating myself for the clicks. And sorry, I think it was hilarious. There was like so many levels of nerdery in that thumbnail, and I think Anton did a terrific job of creating that thumbnail. So, for the people who were offended by it, I guess you won't watch this because you left the channel at this point. But whatever, we're gonna have fun, and I don't care. And Anton, when he made the thumbnail, he was like, either you're gonna love this, or you're gonna hate it, and I loved it. So, but the sort of clickbait accusation, I think, is one that's always really tricky, because the reality is that we're on this really competitive platform, which is YouTube, and that we're fighting against people who are using AI to generate thousands of videos a day. Go ahead, go into the search box, type JWST or Big Bang or anything, and then sort by the most recent, and you will just see AI slop for the entire page. Very rarely do you actually see real videos anymore. And this is what we're up against. And a lot of the more popular videos get 10 times more views than we do in actually like doing the reporting, having people work on this stuff by hand, producing hilarious, nerdy thumbnails by hand. This is what we're up against. And so we have to always be thinking about how we can drive the most traffic to our videos. I think, clickbait is when you say something and it is like not true. Like you're lying, or you are deeply over exaggerating what it is that's been found. And I think we try to walk that line. We try to make things very compelling and yet be as scientifically accurate as we can. And we definitely deliver in the videos that we create. But obviously, it's always, up to the eye of the beholder. And for some people, they have a very high threshold for what they think is clickbait. They get it. They're like, haha, good one, Fraser. Other people, they are enraged the moment they see anything that is clickbait. And yet the reality is that if we didn't push the boundaries, nobody would watch our videos at all. Like a tree falling in the forest that nobody hears. So I know this is always going to be an issue that people are going to argue about, and it's fine. You know what? We have fun and we focus on our journalism, and that's the thing that's most important to us. And yet we have to play the game. That's the YouTube game. And so we will keep playing at the best of our ability. And that's why you love us. All right. We'll see you next week.